Hi everyone, my name is Jack Van Welzen and I'm a student in the Mechanical and Aerospace Engineering Department at NC State University. Today I'm going to be giving you all a brief overview of the research project I've been working on over the past year on detecting hidden damage in composite materials. So starting off, what's the deal? Why is this important? As some background, a composite is a material in which there exist multiple phases. Most commonly, composite materials consist of fibers like carbon fiber or fiberglass and a matrix like a polyester resin. The fibers give the composite strength and the matrix holds everything together. Composite materials are quite common in the aerospace industry since they are lightweight yet very strong while being easily customizable to the complex geometries of aircraft. On the top right here, you can see an example of this customizability where different layers of the composite have their fibers oriented in desired strength directions. Unfortunately, one downside of using composites is that some forms of damage can be difficult to see with the naked eye, but could lead to larger failure down the line. Looking at the bottom right here, one such damage is shown. Two composite layers sandwich a large honeycomb core in the center. While the crumpling of the core is noticeable, the dent created is near imperceptible. The green dotted line shows the flat surface before the dent was created, yet the dent is still difficult to spot. Looking at just the surface, this becomes even more challenging. Most methods to detect this damage take large amounts of time and equipment, making them impractical for scanning large aircraft exteriors. This research project was focused on applying a method called laser spectrophotometry to a composite structure to rapidly locate potential regions of damage. So what is laser spectrophotometry, or LSP for short? The left image here gives a general picture of the relatively simple setup. Unlike other methods which require beam splitters and careful alignment, LSP only requires a heat source, a low power diode laser, a commercial CMOS or CCD camera, and a PC for post-processing. The general procedure goes like this. First, the object of interest, in our case a composite panel, is heated to about 60 degrees Celsius with a heat lamp. As the temperature increases, the composite expands due to thermal expansion. Next, the heat sources are removed, allowing the object to return to room temperature. Simultaneously, the laser is turned on, and the camera starts shooting video of the region illuminated by the laser. Typically, when a laser illuminates a microscopically rough surface, which includes most surfaces aside from mirrors, the roughness causes the laser to randomly scatter, forming a laser speckle pattern. An example can be seen on the far left. This pattern normally remains static, but as the thermal expansion reverses and the composite contracts, the roughness also contracts. You can imagine the roughness as many very small peaks and valleys being stretched and squished as the composite is heated then cooled. As these peaks and valleys contract, the laser light scatters in a new way, causing the laser speckle pattern to change. Damaged regions often contract faster than pristine regions, meaning that the speckle pattern near the damage will change faster than in the healthy regions. We leverage this by comparing the first frame in the video to every subsequent frame, looking for which regions change the most quickly over time. This change is quantified using post-processing image correlation algorithms, and regions which have the highest change or lowest correlation are most likely damaged regions. Here are the results. On the top left, you can see the composite panel used in a baseline measurement using an X-ray CT scan, one of the more complicated methods mentioned earlier. The damage detected with this method is the dark spot in the center, outlined with the red dotted line. The other dark spots were just scanning artifacts and were ignored. The three remaining figures are results from LSP. We tested three different image correlation algorithms: mean squared error, or MSE, normalized cross correlation, or NCC, and structural similarity, or SSIM. For all three algorithms, the larger circle is the illumination area of the laser. Inside this circle, the baseline was overlaid as a black dotted ellipse. Evidently, all three algorithms were able to locate the damage quite well. Additionally, all the LSP results only took a few seconds to capture and process, making it near real time. So what are some important takeaways? Firstly, LSP was demonstrated as an effective, near real-time method of detecting hidden damage in composites. However, upscaling this technique would require some additional work. In this experiment, the laser only covered a 50mm by 50mm region. A much larger illumination area would be required to be practical for aircraft inspection. Additionally, based on the effectiveness shown here, there is some potential for LSP to be applied in the additive manufacturing domain. In this field, defects are prevalent as shown by some poor examples in the bottom right. LSP could be extended to help find these defects as they form in the manufacturing process. Overall, LSP showed itself to be quite effective for locating hidden damage in composites with the potential to be extended even further. Thank you all for your time.